Remember previously that we talked about how to find the null and column spaces of some matrix A. And we said that the null and column spaces were the first two of 4 fundamental subspaces. Well, in this video, we're going to introduce the last 2 of the 4 fundamental subspaces, the other 2, and they are essentially the null and column spaces of A transpose. So at this point, we want to look at how to find A transpose and the null and column spaces of A transpose, and then we want to sort of link the properties of those 2 fundamental subspaces to the properties of the null and column fundamental subspaces. So as a reminder, let's just quickly recap what we do when we find the null and column spaces of a matrix A. So let's say we're given a matrix A like this one. The first thing we want to do is put this matrix into reduced row echelon form. To do that, we might start by flipping the first and second rows so that we have this -1 in the 1, 1 position. We could also at the same time multiply through this row by -1 so that this -1 becomes a +1. So if we swap those 2 rows and multiply through by the -1 scalar, then this second row becomes the first row and we get 1, 0, -1, +2, and then 2, 1, 1, 0. So we did a row swap and we multiplied through by a scalar in one step. Now we want to take 2 of the first row away from the second row to get a 0 here in the 2, 1 position. So the first row will stay the same, 1, 0, -1, 2. And then for the second row, we'll get 2 minus 2 times 1 is 0. 1 minus 2 times 0 is 1. 1 minus 2 times a -1 is 1 minus a -2, or 1 plus 2. That gives us a 3. And then 0 minus 2 times 2 is going to be -4. Now the matrix is in reduced row echelon form, and what we want to realize is that we have a couple of things going on here. First of all, we have pivot columns for our first 2 columns because we have our pivot entries here of the +1 and the +1. And then the other 2 columns don't have pivot entries. These are free columns. And so if we think about these columns as representing variables, so let's say we have x1, x2, and then we have x3 and x4, we can say that x1 and x2 are the pivot variables and x3 and x4 are the free variables. From this matrix, we can pull out a system of equations. So we'll get x1 minus x3 plus 2x4. And if we're trying to find the null space, we set that equal to 0. We would have augmented this matrix with a column of zeros with the 0 vector. And so we get this equation equal to 0. And then here we would get x2 plus 3x3 minus 4x4. And that would be equal to 0 from the second row. We want to solve this system for the pivot variables. So we need to solve it for x1 and x2, which means our system will become x1 is equal to positive x3 minus 2x4, and then we'll get x2 is equal to -3x3 plus 4x4. Now we have everything we need to find the null and column spaces. So let's start building a table because this table is going to be really important to us as we go through. So here's what we know from this table. Let's first talk about the column space. So we have the column space. We know that we call the column space C of A, as in the column space of the matrix A. And we know that the dimension of the column space is always going to be given by Rm. Remember, when we start off with a matrix, we say that the dimensions of the matrix are m by n. In other words, it has m rows and it has n columns. So in Rm space for this particular matrix, we've got 2 rows. That means we're talking about m equals 2. That means the column space is defined in R2. So the column space is in 2-dimensional space. So the dimension, and remember the dimension of the column space specifically is called the rank. We know that that's always equal to the rank, which is the number of pivot columns in the reduced row echelon form of the matrix. We found 2 pivot columns here, one for x1 and one for x2. So we have 2 pivot columns, 2 pivot variables. That means the rank of this matrix is 2. So the dimension of the column space is 2. That means we need 2 vectors to form the basis for the column space. And in fact, we know that that's true because the fact that we have these 2 pivot columns here tells us that we can go back to our original matrix A And because the two pivot columns are these first two columns, we can grab the first two columns of the matrix A, and they will form the basis for the column space of A. So we can say that the column space is equal to the span of the first two column vectors from the matrix. So that's the span of 2, -1, and 1, 0, which is that second column. So what we can see here is that we have two-dimensional vectors. So because we have two vectors, that means that the dimension, the rank, is 2, and they're both in R2. That's why the space in which the column space is defined is R2, because these are two-dimensional vectors. In other words, the fact that we have two-dimensional vectors, 2 dimensions, so 2 vectors in 2 dimensions, is given by 2 vectors in 2 dimensions. That's where we get that from. So the column space is defined as the span of the columns that were indicated by these pivot variables. And then the null space, so we'll say the null space, we call it the null space of A. And the null space is always defined in our n space, where n is the number of columns in our original matrix. So we have 4 columns in our original matrix, so the null space is defined in R4. And the dimension of the null space, which remember we also call the nullity, is always equal to n minus r, again where n is the number of columns and r is the rank or the dimension of the column space. So in this case, we would say 4 minus 2, or just 2. In other words, we need 2 vectors to span the null space of A. And that makes sense because if we look here at the equations that we built for the pivot variables, and we pull those into a null space, we can say that the null space is the span of the 2 vectors given here. And so if we pull this out of this equation, we get here x1, x2, x3, and x4. We take our free variables, x3 and x4, the variables on the right side of this equation, or the free variables here that we've boxed in blue, x3 and x4. So x3 and then x4, so plus x4. And we build these vectors out. So we know x1 is equal to 1x3, so 1x3 minus 2x4, so minus 2 for x4. x2 is equal to negative 3x3 plus 4x4, so positive 4. And then x3 has to be equal to 1x3 and 0x4. And x4 has to be equal to 0x3 and 1x4. So this dimension, this nullity of 2 here, tells us that we need 2 vectors to form the basis for the null space of A. These are the 2 vectors right here. So we take these 2 vectors and we say that the null space is given as the span of 1, -3, 1, 0, and the second vector here, which is -2, 4, 0, 1. So the null space is spanned by these 2 vectors, and what we see is that we have 2 vectors here, that's the dimension, in R4, that's the space R4. So we have a 2-dimensional surface in R4. Think of that as a 2-dimensional plane sitting in R4. That is the null space of the matrix. Now when it comes to finding the null and column spaces of the transpose, of course the first thing that we want to do is find the transpose of the matrix A. So we'll look at A transpose, and of course that's going to be A transpose is equal to, because here we had a 2x4 matrix for A, we're going to end up with a 4x2 matrix for A transpose. That's going to be 2, 1, 1, 0, and then -1, 0, 1, -2. So that's A transpose. And now remember we said we're just finding null and column spaces for the transpose. So let's think first about the column space of the transpose. Well, if I'm looking at the column space of the transpose, these columns are the same as the rows of A. And so because these columns are the same as the rows of A, when we say the column space of the transpose, we also call that by a different name. We call it the row space of A. Because remember, the column space of a matrix is all the possible linear combinations of the columns of the matrix. So if I'm saying that the column space of the transpose here is all the possible linear combinations of these 2 columns here, that's the same as all the possible linear combinations of these two rows up here. So when we define these four fundamental subspaces, we always relate their names back to the original matrix A, not A transpose. So we're going to call the column space of A transpose, we're actually going to call that the row space. So if we call this the column space, if we call this the null space, then this is the row space, and it is the column space of A transpose. So we call it the row space, but we write it this way, the column space of A transpose. So just think about the row space of the original matrix A is the same as the column space of A transpose. And as it turns out, its dimension is always going to be in Rn space, which we already know is R4 because our original matrix has 4 columns. And its dimension is actually always going to be equal to the rank of the original matrix. It's always equal to the dimension of the column space, the dimension we found up here, which was 2. The row space and the column space of a matrix always have the same dimension. So how would we actually go about finding the row space? Well, again, we're dealing with A transpose here, so we would start with A transpose. We want to get this into reduced row echelon form. So if we put this in reduced row echelon form, let's first go ahead and switch the first and second rows. So we'll get 1, 0, 2, -1, 1, 1, 0, -2. And then let's go ahead and subtract 2 of the first row away from the second row. So when we do that, we'll get 2 minus 2 times 1 is 2 minus 2, or 0. Then we'll get -1 minus 2 times 0, that's going to be a -1. Let's subtract the first row from the third row. So we'll get 1 minus 1 is 0, and 1 minus 0 is 1. And then we'll have 0 and -2. And then let's go ahead and switch the second and third rows. So we'll have 1, 0, 0, 1, 0, -1, and 0, -2. And now, if we go ahead and keep our first and second rows the same, 1, 0, 0, 1, we'll add the second and third rows to get the new third row. That'll give us a 0 row. And then we'll add 2 of the second row to the fourth row, and that'll give us another 0 row. So this is the reduced row echelon form of the transpose. So what do we see now here? Again, we go back to the same process we used for the original matrix. What we see is that we have 2 pivot columns. Both of these columns have a pivot entry. So we can say that this is x1 and this is x2. And this makes sense because remember that the dimension of the column space came from the number of pivot columns in A. Well, the dimension of the row space then, of course, is going to be given by the number of pivot columns in A transpose, and we've got 2 of those. So this tells us that if we want to define the basis for the row space of A, for the column space of A transpose, we can use the first 2 columns of A transpose. Both of these are pivot columns, so we use both columns from the original matrix. Let's go ahead and move this down a little bit so that we can line this up. And then what we have here for the row space, we say that the row space is the span of the first 2 columns of A transpose, which of course is just both columns of A transpose. So 2, 1, 1, 0. And then the second column, which is -1, 0, 1, -2. And so this is the column space of A transpose. It's all the linear combinations of these 2 4-dimensional vectors. So again, because we've got 2 vectors, that means they're forming a plane. The dimension is 2, so they're forming a plane, but they're in R4. So they're a plane in R4. The row space is defined as a plane in R4 space. And then finally, when it comes to, let's move this down, when it comes to the null space of A transpose, there's something important that we want to say about its name. So we know that the null space, the original null space up here, of course we know it's the set of vectors that satisfy A times the vector x equals the 0 vector. Well, the null space of A transpose is then going to satisfy this equation. We'll say A transpose times the vector x equals the 0 vector. Any vector x that satisfies this equation is going to be in the null space of A transpose. Well, what we realize is that we can actually put this equation back in terms of the original matrix A. If we take the transpose of both sides of this equation, so we'll transpose both sides. Remember, here's a rule that's going to come in handy that we learned before. When we take the transpose of a product like this, we can distribute this transpose across the values inside the parentheses here, as long as, remember, we have to flip the order. So this actually breaks down into the vector x transpose times A transpose transpose. So we just flipped the order of these two, but we distributed the transpose. That's equal to the 0 vector transpose. Remember also that we learned that the transpose of the transpose, those two things cancel out. A transpose transpose is just A. So this equation actually becomes the vector x transpose multiplied by the matrix A. Now we're back to the original matrix A instead of A transpose, and that's equal to the 0 vector transpose. The fact that we were able to simplify the null space equation for A transpose down into this equation is why we call the null space of the transpose the left null space. So instead of calling it the null space like we do for the original matrix A, we call the null space of A transpose the left null space simply because of the fact that this vector here moves to the left-hand side of the matrix A. So in this equation, which is what we normally see, we have the matrix and then the vector is multiplied on the right-hand side. So the matrix A times the vector x, the vector's on the right-hand side. Here, we have the vector on the left-hand side and then the matrix. So the vector x transpose times the matrix A. And because that vector's on the left-hand side, we call it the left null space. But left null space just means the null space of A transpose. So that's our name for it. This is where it comes from. Of course, it looks like this, the null space of A transpose. That's how we abbreviate it. And it is always going to be defined in Rm space, just like the column space. And of course, we know that that's already R2 because we found it up here and because the original matrix A had 2 rows. All these spaces are coming from the rows and columns in the original matrix when the matrix is an m by n matrix. That being said, the dimension of the left null space is always equal to m minus r, the number of rows in the original matrix minus the rank r. So in this case, we had 2 rows and our rank was 2. The dimension of the column space, or the rank, was 2. So we get here 0. So the dimension of the left null space is 0. What exactly does that mean when we say that the dimension is 0? Well, it just means that the space is made of only the 0 vector. In other words, a plane has 2 dimensions, a line has 1 dimension, the 0 vector has 0 dimensions. And of course, we can see that if we go back to the reduced row echelon form of A transpose, we come back to this matrix here. If we were trying to find the null space of A transpose, we would have augmented this reduced row echelon form with the 0 vector, and we would end up with, because we have the x1 and x2, we have the 1 and the 1 right here, we would end up with 1 times x1 equals 0, and 1 times x2 equals 0. We would get those two equations from the first 2 rows of the reduced row echelon form. And so this would tell us then, let's go ahead and move this down again so that we can line it up. So we have the left null space here. So this here tells us that the null space of A transpose is equal to the span of this vector here turns out to be x1, x2 equals just the 0 vector, like this. So we just get the span of the 0 vector, which of course is just the 0 vector, so we could say that this is just equal to the 0 vector, or just equal to, instead of saying the span, just the 0 vector, like this. And of course this makes sense as well, because the dimension of the null space is always given by the number of free variables that we have in the matrix, And when we were talking about the matrix A, we had two free variables, x3 and x4. The dimension of our null space was 2 because we had those two free variables. But with A transpose, we have no free variables. We weren't able to box in blue any free columns, so we had no free variables at all, which means the dimension of that null space was going to be 0, which just leaves us with the 0 vector. So hopefully you're starting to see how the way that we found the null and column spaces and these properties of the null and column spaces carries over exactly to how we find the null and column spaces for A transpose and the properties of those null and column spaces. We just have to remember that when we switch over to A transpose, our column space of A transpose is now called the row space, and the null space of A transpose is now called the left null space. And then we can just proceed on with finding the column space of the transpose and the null space of the transpose. And from these results, we're able to get the space and the dimension, because again, we can see here that we have a 2-dimensional space in R1, 2, 3, 4. So a 2-dimensional space in R4. And here we just have the 0 vector in R1, 2 space. So we have a 0-dimensional space in R2 space.